Okay, today we're going to talk about what is known as arithmetic sequences. Arithmetic sequences are patterns, and they're numbers that are patterns that relate to linear equations. So since we've figured out how to write linear equations pretty well, uh, arithmetic sequences we'll find out follow a typical pattern. And as we take a look at sequences, there's set numbers. For instance, we refer to them as different terms: first term, second term, third term, fourth term. You'll see these numbers follow a set pattern. You see these terms in the sequence increase by 2 every time. So if it were to pattern continues, the numbers would just increase by 2 every time, which we'll see is similar to a linear pattern. So let's take a look at how this works. So as I mentioned, a sequence is an ordered list of numbers. Those numbers in the sequence are called terms. In the arithmetic sequence, the difference between the consecutive terms is always constant, whereas sequences in general, they can just follow any kind of pattern, but arithmetic sequence the difference is constant, and that constant difference is known as the common difference. It's a terminology we'll use. So when we refer to arithmetic sequence, we use the form a sub 1. That refers to the first term. So a sub 1 plus d, so first term plus the difference. A sub 1 plus 2d, meaning I take the first term and I add the difference twice to get to that third term. So the terminology we use that sub 1 to represent the first term, or sub 2 to represent the second term. For instance, if a sub 1, the first term is 2, the difference is 6. We know it's 2, then 2 plus 6, then 2 plus 2 times 6, for example, are 2, 8, 14. And that's an arithmetic sequence because we're adding a common difference. So take a look at these two patterns, see if you can figure out the pattern, and then determine if it's arithmetic. Pause the video and restart when you're ready. Okay, so the pattern in the first sequence, we see the numbers are increasing by 5. So the next term would be 21. The term after that would be 26. And that would be an arithmetic sequence because we have a common difference of 5. We're adding 5 every time. The next pattern, we have 3 to 5 is adding 2, then we add 4, then 6, and 8. So we can see there's a pattern to this sequence. They're increasing by 2 more every time. So the next one would increase 10 to get 33, then by 12 to get 45. So there's a pattern for this sequence, but it is not arithmetic because there's not a common difference. The difference between the terms is changing every time. Okay, so let's graph a sequence now. So when we graph the sequence, we make the x value its term number. So for instance, in this sequence that we have here, this is the first term, so it'd be a sub 1. 1 is the second term, a sub 2, a sub 3, a sub 4, and 16 would be the fifth term. Okay, so we can graph those points by saying, well, the first term is -4, and the next term is 1, 6, 11, and 16. So 1 is the second term, 6 is the third term, 11 is the fourth term, and 16 is the fifth term. Okay, so once we plot those points on our graph, we can take a look at what's going on here. Is this a function? Well, does each input have an output? Looking on the graph, we can check the vertical line test, and it appears that each input has an output. So yes, this would be a function. And if it's a function, that would mean we can write an equation for it. So let's see how we can do that. Let's just look at the sequence in general. First of all, what's the common difference? How much are they changing? Well, it's the same one we looked at before. These are increasing by 5 every time. So the common difference would be 5. Okay, so these all go up by 5 every time. Now, looking at the graph, what's the slope? Well, slope is difference in the y and the difference in the x. Well, the x's are increasing by 1, so it's changing 5 in the y for every 1 in the x. And I can look on my graph and see the same thing. So you go from one point to the next, it goes up 5 over 1. So my slope would be 5 over 1, which I could simplify as 1. Okay, so we can see that connection between the common difference and the slope. Sequence the common difference means about the same thing as slope in a linear equation. So if I wanted to write this in slope-intercept form, I'd say y equals mx plus b. And if I wanted to write the equation, go ahead and figure out what that equation would be and restart it when you're ready. Okay, so hopefully you found the equation in slope-intercept form. So I took the slope, which we said was 5, substituted that in, and then I took one of the points. I chose 1, -4, since that was one of the easier ones that had smaller numbers. You could have used a different point, but I plugged in 1 and -4 for my x and y values. Then I used that to solve for b. So you can see the work that I did. I got b is -9. So then I put that back into the original equation, y equals mx plus b. Y equals 5x minus 9. So we could take a look on the graph. Well, does that fit? My y-intercept, -9. Sloping up 5. 1, 2, 3, 4, 5 over 1. I could draw a line through those. And that equation seems to fit the pattern for my sequences. So hopefully you can see that connection between the linear equation and arithmetic sequences. So arithmetic sequences are really a linear pattern, and we can create an equation for it. But the only difference with sequences is we're just looking at specific terms. We don't include, every real number in between these values. We just look at specific points on the graph. So let's come up with a rule. So as we mentioned, the common difference is like the slope. And, in this case, since we're talking about the first term in the sequence, there really isn't a y-intercept because there wasn't a 0 term. There could be, but generally the sequence, we start in the first term. So in taking a look at that, we write a rule similar to the y equals mx plus b. So the nth term, this is known as the explicit rule. We call it that because we can find each exact term, so the nth term, and we take, this is similar to our y-intercept, our first term, because that's our starting point in a sequence, plus the slope, the common difference, times n minus 1. Before we said y equals mx plus b. Here, our x that we're multiplying by is n minus 1, because if I want to get to the fifth term, well, how many times did I add our common difference? 4 times, because I started at our first term, and I added 5 once, twice, 3, 4 times. To get our fourth term, I added the common difference 3 times. 1, 2, 3. Third term, I added the common difference twice. Second term, I added the common difference once. My first term, I don't add my common difference any times. So it's always 1 less than the number of term. The recursive rule, that's just showing what the pattern is. So if I define my nth term, I just take whatever the previous term was, so the n minus 1 term. So for instance, if I want to find the fifth term, I need to know what the fourth term was, and then I add the common difference. So recursive rule is more for how do I write the next term in the sequence. So let's take a look at this sequence again. -4, 1, 6, 11, 16. I'm going to write the rule for the nth term. So once again, we said this common difference is 5, because that's what we're doing each time. We're adding 5. And then let's look at some of the different terms that we have. So the first term, a sub 1, is -4. Okay, so when we're going to write the rule, because we want to find the 100th term, you don't want to keep adding 5 99 times. That's just going to take forever. So let's just start off with our recursive rule. See if you can write that. So I'm just going to abbreviate recursive rule. So to find the nth term, well, I take the previous term, and what am I doing each time? Well, I'm adding 5 every time in this sequence. So I'm going to take the previous term, and I'm going to add 5. So first term is -4, I add 5. Second term, well, -4 plus 5 is 1. I could keep going down the line until I get the 100th term. Like I mentioned, that's going to take a long time. This rule works nice if I just want to find the next 2 terms in the sequence. Well, 21, 26, because I just add 5 to the previous term. Okay, so let's take a look at the explicit rule. And how do we write that one? Well, for the explicit rule, we take a sub n, so the nth term is equal to a sub 1, the first term, which was -4, plus n minus 1, because I'll add my common difference that many times, times d, and my common difference is 5. Keep in mind that this order can be switched around. If you want to put 5 times n minus 1, that's fine. Multiplication is commutative. So how do we use that to find the 100th term? Well, I say a sub 100, the 100th term, is equal to -4 plus n minus 1, well, n is 100 because it's the 100th term, 99 times 5. I'll let you calculate that quickly. Pull out your calculator and figure out what the 100th term will be. And maybe you don't need your calculator for that. Maybe you can solve that mentally. 99 times 5? Well, I know 100 times 5 is 500, so I want 1 less. So it's going to be 495, 1 less 5 is 495, plus a -4 will give us 491. Okay, so hopefully you'll see that finding the 100th term, or whatever term number, is a whole lot easier when you use the explicit rule. But the recursive rule is important to use when you're just finding the next term in the sequence. You don't have to go all out and find the whole explicit rule. You just figure out what's the common difference, what do I do each time, just add that to the previous term. Alright, so that's what we learned about sequences today. We learned how to write the recursive rule and the explicit rule, and we learned that in an arithmetic sequence, there's a common difference. The same number needs to be added every time. And we related that to a linear function and found out that really the common difference is the slope. So take some time to practice looking at what an arithmetic sequence is as you work through the practice problems. We'll see you next time.